Hey guys, this lesson is 9.4 for Calculus BC, and we're going to be talking about comparison test. So for the convergence test that we've learned already, they have specific details, like the integral test has to be a function that has an easy antiderivative, or the p-series or geometric. They have a specific setup, right? So when things start to get a little more complicated and they deviate from looking exactly like one of those tests, for example, this one says 1 over 2 to the n is clearly geometric, but because this one adds the variable n to the top, although it looks alike, it's not geometric. Okay, and this one is clearly p-series, but because this one adds a +1 to the denominator, it's not, right? So these comparison tests are going to allow us to be able to solve these. Even though they're not geometric or p-series, we're going to compare them and then be able to find out if they converge or diverge. So we have the direct comparison test and then the limit comparison test. Let's look at direct comparison test, okay? We're going to talk about two different series, a sub n and b sub n, where a sub n is going to represent the smaller value, okay? And b sub n is going to be the greater one. So I've put it to you in the notation as a textbook. I've put it to you in words. And then I'm going to give you an analogy to help you understand this, okay? So if we are testing the larger one, b sub n, and it converges, then we can prove convergence for the smaller one. But it does not work the other way around. The other way around only works for divergence. If we can prove that the smaller amount diverges, then the series of the larger fraction also diverges. And again, we cannot prove this the other way around. Okay, so if the larger converges, then the smaller also does. If we can test that the smaller diverges, then the larger also. So here's a quick little, you can either memorize that or hopefully this analogy will make some sense to you. We're going to imagine that this series is represented by a race, okay? And the smaller series is going to represent a slower runner, and the larger series is going to represent a faster runner. So if we start the race and we talk about a stop point, okay? If we can say that the faster runner has to stop, right? Then we can also say that the slower runner definitely is going to have to stop too if he's slower, right? Okay, he's going to get tired faster. And stopping would be like stopping at a number at converging. Okay? Now, if the slower runner has to stop, it doesn't mean anything about the faster runner. He's ahead. We can't prove that he had to stop or converge. Okay? Now, if we talk about finishing the race, let's talk about that as divergence. As going to infinity, going all the way. We know that if the smaller runner diverges, makes it to the end of the race, we can assume that the faster runner also did so. But if we're only talking about the faster runner making it to the end of the race, we cannot prove whether the slower runner made it to the end or not. Okay, so hopefully that makes a little more sense. If not, bear with me. Let's look at these examples and see how you feel about it. Before we start this example, I want to give you a quick little side note. When we're comparing fractions, you want to analyze obviously the numerators and the denominators. A smaller numerator is going to represent a smaller number, right? A larger numerator represents a larger number. That we know. But a lot of times the change is going to happen in the denominator, okay? So if I end up with a smaller denominator, right, that's going to represent a larger number. And a larger denominator, think of the bottom keeps getting bigger, bigger. That's a bigger fraction, which means a smaller number. So when we look at this first example, it appears to have a part of the geometric because of this 1 over 3 raised to the n, but this +2 is what's going to force me to use the comparison test, right? So I can compare it to the infinite series of 1 over 3 raised to the n. Okay, now that is geometric. My next step is to figure out who is bigger. Well, if this denominator adds 2, it means this denominator is bigger than this one. And if this denominator is bigger, right, larger denominator, that means that this is a smaller number. Okay, so the original is less than what I'm using to compare. So if what I'm using to compare is the larger series, I said in the last part of the notes that I could only test for convergence, right? So let's move on. If I get divergence, that means I have no conclusion. If I get convergence, then I can stop. I'm going to rewrite this, like I learned in the geometric series, as 1 over 3 raised to n, okay? That means for geometric, okay, my absolute value of r is 1 over 3. And because that is less than 1, then this series converges, okay? So I said because I was testing the larger, I could only test for convergence. Since I came out with convergence, I can conclude that because this series converged, and it was larger, therefore, the original also converges. And I'm done with this one. This next question is talking about the infinite series of 1 over 2 plus square root of n. Now, if I was talking about 1 over square root of n, then that's going to look familiar. That would look like a p series, okay? So let's compare it with the infinite series of 1 over square root of n, okay? Now, if this one is adding a 2, that means it's going to be a bigger denominator, which makes it a smaller number, okay? So if the one that I'm testing is the larger number, okay, or larger series, I'm sorry, that means that I'm going to test, I can only test for convergence, okay? And we said that this one looks like P series. So moving on, let's rewrite this as the infinite series of 1 over n to the 1/2. According to P series, my P, which is 1/2, is less than 1, which means that it diverges, okay? So if this diverges, but I said I could only test for convergence, right now I have no conclusion, and I need to try another test. Okay? So you're not completely stuck here. We have more options, okay? I'm just going to try something different, okay? One of the ones we talked about was just 1 over n. So we tried this one, and it did not work. Now let's try comparing. I'm going to rewrite my original. And I'm going to try and compare it with that harmonic series, which was 1 over n. All right, now I'm comparing it here. If we're going to start comparing numbers, I don't want you to try comparing with something small like 1, okay? Because remember, the further in the game these numbers are, the more it's going to tell me about what's going to happen when I start to add them all together. So try a big number, like let's say 25. 1 over 25, or 1 over square root of 25, which is 5, plus 7. I mean, excuse me, plus 2, which is 7, okay? I'm obviously going to end up getting bigger denominators over here on the right side, which means that this one on the right is going to be a smaller number, okay? So now that I proved, which this one's harmonic, okay, now that I proved that I'm working with the smaller series, right, I can test for divergence, okay? And now, if you start to have these memorized and you recall, you know that a harmonic series diverges, okay? Okay, so if I was testing for divergence and I get divergence, now I can make the conclusion, right? Let's rewrite it. that the original series, right, because this is just answering that this one diverges. We need to make our conclusion that 1 over 2 plus square root of n diverges. Right, again, this only worked because I was looking for divergence and I got divergence. So now I have my final answer that it diverges. We're now moving on to the limit comparison test. This is a test you're going to want to go to if your direct comparison test does not work. So for example, we're testing for divergence and we keep getting convergence and you can't really simplify the equation anymore, then here's where you want to go, okay? So we have 3 things to look at. One, we need to make sure that both series that you're using to compare are positive. Then you want to test the limit as n approaches infinity of a sub n divided by b sub n. A sub n is the given, b sub n is the one we're going to be using to compare. So original divided by the one we're picking to compare. Your limit should give you an answer, right? If it gives you an answer L, L is going to represent any number between 0 and infinity. If your limit gives you 0, you can only test for convergence. If it gives you infinity, you can only test for divergence. If it gives you an L, a number in between 0 and infinity, then you can test for either, okay? Then once you've proved that, step 3 says that the answer of the series for b sub n, the one you're using to compare, will then tell you the convergence, divergence, or either of the original being given, okay? Let's take a look at an example. This first question is the infinite series of 1 over 2 raised to n plus 1. I know that this looks a lot like 1 over 2 raised to the n, which is a geometric, right? Remember, we are always starting with a direct comparison. If it doesn't work, then we go to limit comparison. Okay, so this one adds the plus 1, which makes us have a bigger denominator, which makes this the smaller number. Okay, so if I'm working with the larger series, oops, that means I can only test for convergence. Okay, so let me go ahead and test it. I forgot to put my little 1 up here. Remember, I can rewrite this as half raised to n. And so that means that my r, according to geometric, absolute value of r, I'm sorry, is half, which is less than 1, which means this one converges. Okay? If I could only test for convergence and I come out with convergence, that means that the original that I was talking about also converges. All right. So on this question, because direct comparison worked, we don't have to move on to limit comparison. Let's analyze this next one. Very similar question with one small difference. We are subtracting 1 in the denominator, okay? So same comparison. Which is geometric, right? But now, if this denominator is taking 1 away, that means this denominator is going to be smaller, which means this fraction is going to be larger, okay? And maybe you start seeing where this is already going. I'm testing the smaller, which means I can only test for divergence, right? And I'm going to rewrite the work, but we just saw on this last one that this, because we're using the same exact one to compare, it does not diverge, right? The r was half, which is less than 1. So this converges, but we had just said that we can only test for divergence. So I have no conclusion, okay? I have to try another test. Okay, so In the last, when we were talking about direct comparison, we tried to re-simplify the equation, right? I can't simplify this anymore. So now is where limit comparison test is going to help me out. So according to the limit comparison test, I'm going to still compare these same two, okay? Which means first I have to check that they are both greater than 0, okay? So if this is an FRQ, it's a little lengthy to write, but you have to say that both of them are positive. They're both greater than 0. Check mark, okay? Step 2, I now want to check the limit as n approaches of infinity of the original divided by the new one that I'm working to compare, okay? Now, a fraction divided by a fraction, you can write them next to each other. And now maybe you feel more comfortable doing a keep, change, flip. Right? We multiply by the reciprocal. If you feel like you can do this step faster, feel free to do so. I just want to walk you through it. Right? So when I solve this, I get infinity over infinity, which means I have to do L'Hopital's. Okay? So I'm doing the limit as n approaches infinity. The derivative of this exponential function is a rewrite times ln of the base times derivative of the exponent, which is 1. Same for the bottom. And derivative of that minus 1 is 0. These cancel out, and I'm left with the limit as n approaches infinity of 1, which is just 1 because they reduce, right? So because 1 is a number between 0 and infinity, I can test for either, right? So that's a nice thing because whether I get convergence or divergence on this last step, I am done. Okay? Step 3. The one that I was working to compare is 1 over 2 to the n. Okay? I can rewrite that as half raised to n. And now I can clearly see the geometric series where the absolute value of r is half, which is less than 1, which converges. Okay? So I was allowed to test for either, and I got convergence. So now I can say, therefore, the original, which is 1 over 2 raised to n minus 1, also converges. This next question is the infinite series of 2 raised to n divided by 3 raised to n minus 1. So I can compare this with, take off that little minus 1, and I have 2 raised to n over 3 raised to n. And this could also be rewritten without changing it as 2 over 3 raised to n, and we can see that this is geometric. Okay? So now when I compare these two, since this one subtracts 1 from the denominator, it makes it a smaller denominator, which makes it a bigger number. So if the one that I'm testing is smaller, right, I can only test for divergence. Okay? If I test this geometric, I can see that my R is 2 over 3, which is less than 1, which means that this series converges, okay? But if I could only test for divergence and I get convergence, then I have no conclusion and I have to try another test. So let's move on to limit comparison, okay? First, I need to state that both the original and the one that I'm comparing, whoops, trying to go too quick here, are both greater than or equal to 0, okay? They're both positive. Then I have to test the limit as n approaches infinity of the original divided by the one I'm working to compare, which I can rewrite these cancel. And now maybe you're getting used to this. You've seen it several times, maybe just happening with different numbers. So I'm going to use L'Hopital's. And now I'm working with the limit as n approaches infinity. The derivative of the top is an exponential function. So I have rewrite times ln of the base. Same thing happens in the bottom. And then derivative of -1 is 0. So all of this here cancels again. And then limit of 1 is just 1, right? So 1 is a number in between 0 and infinity. So I can test for either convergence or divergence, okay? Which is always a nice thing. Now on step 3, which we technically already did up here, according to my comparison by geometric, my R, is 2 over 3, which is less than 1, so it converges. And since I can test for either, that's okay. I can just state now that my original also converges. And I'm done with that one. Let's see one last example, okay? I'm going to encourage you to have your calculator out for this one. This last question reads the infinite series, right, of 2n plus 5, and then I have two binomials here on the denominator. So I'm going to take a minute and rewrite this. I'm not comparing yet. I just want to rewrite this as 2n plus 5. And then this down here gives me an n squared minus 5n plus 6, right? It's going to be easier to compare. So now if I'm comparing, okay, let's go down here. Just like in the horizontal asymptote rule, I'm just going to use these first two terms to compare, right? So if I'm comparing, I'm going to say 2n over n squared, and that reduces to 2 over n. And we said that anytime we have a coefficient, we are allowed to bring that to the front. And I'm really working with 1 over n, which this is harmonic. Okay? So if I look at my original and compare it to the new one, okay, even if I take out this 2, I want to start testing who's bigger here. And there's a lot more going on, so feel free to take out your calculator. We can say, try any number. And again, try a bigger number. Don't start something like 1, 2. If we say, let's say 20. If we plug this into our calculator, we get that the original okay, this is going to give me, just checking it at 20, we're going to have about 1.47 if you put that in your calculator. Okay, and now if we're checking this harmonic series, right? And again, we're not solving the series here. We're just checking what it would be at 20 to see who's bigger. This gives us, I'm sorry, I put the decimal in the wrong spot here. This is 1.47. This one gives me 0.1, okay? So we can say that the original is bigger than the one that I'm testing. So if I'm testing smaller, I can only test for divergence, okay? Which, if you're already starting to memorize these, which I always encourage you to, if you have this memorized, you know that a harmonic series always diverges, okay? Now, if I was testing for divergence and I come out with divergence, I can make the conclusion that the original, and you can write it either way, also diverges. So by direct comparison, I was able to come out with a conclusion, so I don't even need to go to the limit comparison test, okay?